Now let's get the idea for the proof of correctness of Kruskal's algorithm by looking at our earlier example. So recall what Kruskal's algorithm is going to do. It's going to consider these edges by increasing weight. So we're going to add in these first 5 edges. The 6th edge we're going to skip because it creates a cycle. Then we add in these 5 edges of weight 7. And then finally we're going to consider one of these edges of weight 9. Now which edge of weight 9 do we consider first? Well, that's an arbitrary choice. Let's suppose we consider this edge of weight 9 first. Let's mark the endpoints as V and W. Now in general, how are we going to prove that this algorithm is correct? Well, we're going to do it by induction. So let's suppose that the algorithm is correct so far, so that the current X is correct so far. What does that mean to be correct so far? That means that these edges are part of an MST. So there is an MST T, and X is a subgraph of T. So we're on our way to an MST, to a solution to this problem. So we're assuming that these red edges, which I've now highlighted as green edges, are part of an MST. Now let's suppose that we add this edge that we're considering right now to this subgraph X. If we don't add this edge to the subgraph X, then X is still part of an MST. But if we add this edge E to this subgraph X, then we want to make sure that X union E is part of an MST. And that's our claim that we're going to prove. We're going to prove that X union E is part of an MST T prime. T prime might be different than T, so we might be heading in the direction of a different MST than we were headed for before. But we're still on our way to an MST. Now, what is the key property that ensures that adding E to X ensures that we're still on our way to an MST? Well, when are we adding this edge E to X? Well, we look at the component containing V, which are these 6 vertices, and we look at the component containing W, which are these 2 vertices. These are different components. Therefore, we can add this edge and it doesn't create any cycles. Now, the key property is that if we consider one of these components, let's say the component containing V, and we let S be the set of vertices in the component containing V, and S bar is the complement of this set, so that's the rest of these vertices, then the key property is that our current subset X has no edges which go from S to S bar. If there was an edge that goes from S to S bar, then that vertex in S bar, which is connected to S, would be added into S. So it would be in the component containing V. This component is a maximal set, so we know that nobody in S bar is connected to anybody in S. Therefore, there are no edges of X going from S to the rest of the graph. That's the definition of a component. So X has no edges that go between S and S bar. So X doesn't cross between S and the rest of the graph, S bar. But this edge E does cross between S and S bar because V is in S and W is not in S. Now, what is the key property about E? E is a minimum weight edge crossing from S to S bar. Now, there are several edges of minimum weight crossing between S and S bar, 2 in particular. We can take any of those minimum weight edges. For any minimum weight edge crossing between S and S bar, if we add E to X, then X union E will be part of an MST. That's what we're going to prove. And we're going to prove in general that if we take a subset of edges which are part of an MST, and we take an edge which crosses from S to S bar of minimum weight, and no other edges of this current subset cross from S to S bar. So this is the minimum weight edge crossing from S to S bar. Then we can add this edge into our current subset, and that'll still be part of an MST. This general claim will be known as the cut property. Before we go ahead and formalize the cut property statement, let me formalize what I mean by a cut, this partition of vertices into S and S bar.